Hello, Alien Worlds. Welcome to the second office hours. We're going to finish setting up here for about 2 minutes, and then we'll be live and good to go. So please write in your questions. There's a question and answers kind of tab in the Google Hangouts, and we'll get to your questions and answer them. So bear with us for 1 or 2 more minutes, and then we'll get started. No viewers.
Do you have headphones again? I can go get mine just so I make sure everything's working.
Ready to go? Yeah, do turn them on.
Oh.
Yeah? Okay. All right, let's begin. Aurora will start feeding me questions. So remember to write them in if you're joining us here live.
Do you want to go for the discussion
Yeah,
questions?
let's do that.
Okay. So our first question is, can you explain how you actually process spectra to quantify the elemental composition of stars? Please include how the rotation speed of stars will smear the absorption lines, is how it is handled.
Oh, excellent. Okay, so the question is about how do we actually process spectra when we're doing this at an observatory. So the first thing is you actually have to take a spectrum of, say, a star. Well, that's probably the simplest thing to talk about in this case. And so what you do is you have a device that's attached to the back of your telescope. That device kind of separates the light and then smears it into its composite colors. We call that usually a diffraction grating. And from that, usually we have to do a bunch of different things. We have to usually take a look at something that we know the exact wavelengths of light of, so that we can know, right at this location in our spectrum, it's exactly this wavelength, and right at this one, it's this wavelength. And so what we often do is we actually look at tubes of gas, that we actually have a tube that's a glass tube that's full of, say, helium or neon or argon. In the optical, those are probably the 3 most common ones that we use. And we run electricity through them, which actually super excites all of the electrons. They get up to a very excited state, and then as they fall down, just like you maybe saw in the demo that we did, they jump down off those platforms, and as they do that, they emit light at very specific wavelengths. And so we turn those on in between looking at, say, a star, and then we know exactly the wavelengths of light. So we have to calibrate our wavelength. That's one thing we have to do. The other thing we have to do is calibrate the flux, how much light is coming, because it turns out detectors are like a camera is sensitive to different amounts of light at different wavelengths. And so we have to look at a star that we already know what the answer is. And so we do that. We look at what we call a flux calibrator or a flux standard. And that allows us to actually understand how much light is coming at a function of wavelength, and actually also at different parts of our detector. So we do that, and we get a spectrum of a star. Actually, Aurora has one, at least, that's looks a lot like a spectrum of a star. Can I actually see your piece of paper in front of you? So Aurora is sitting with me, and she actually has been working on spectra for our research that we do together. And here's actually what we get. And this is a plot of the brightness, essentially, as a function of the color or the wavelength. This actually is for a collection of stars in a galaxy, but if you can see it, there's a bunch of features in here. And so one of the ways those features are different elements, or actually in this case molecules, that are absorbing the light, just like we talked about in the module. And so to actually figure out how much of those in, we actually have to construct a model. We can know something about the physics that's happening, but just seeing sodium doesn't necessarily by itself tell us how much sodium is there. It tells us there's sodium, say, present in the atmosphere of a star, but we have to create a model that incorporates how hot the star is, how dense the star is, in order to actually figure out exactly how much sodium there is. So what we do then is create a model and compare it to our spectrum. And in the end, we get the amount of material that's in the star. Now, the other part of the question was, how do we account for stellar things like rotation? Because if the star is rotating, one side of the star is going to be coming towards you, and it's going to be a little bluer, and one side is going to be going away from you and a little redder. And so that actually will act to broaden the spectral features. For most stars, it turns out that's not a big deal. They're broadened by a very small amount so that we couldn't actually detect it. So unless you're looking at stars at a spectrum that's very, very high resolution, where you've spread the light out a whole lot, for individual stars, that's usually not very important. It's actually one of the techniques we can use to figure out how fast stars are rotating if we have a very high resolution spectrograph. But most of the stuff that I do in my research group, that doesn't matter at all. What does matter, though, is if you're looking at stars now as a part of a larger galaxy, the stars aren't just rotating, they're now whipping around the galaxy at actually very fast speeds, hundreds of kilometers per second. And then you actually have to worry about a star on this side of the galaxy is going away from you, or in this case towards you, at a couple hundred kilometers per second, and on this side is going away from you at a couple hundred kilometers per second, and that actually will really broaden your lines. And so we have to account for that when we actually do the measurements. Was that all of that one?
Yes.
Okay, perfect.
The next question from the discussion forum is, you talked about emission lines as well as absorption lines. Do astronomers use both, and how? Are they for different purposes?
That's a great question. So the difference between emission and absorption lines that we talked about when we were talking about the atomic lines, or the lines that we see in the spectra, the jumping up and down. So yeah, we do use both of them. They're used for similar purposes. I mean, the nice thing about all spectral features is that they really are kind of the fingerprints of elements, or the telephone numbers, if you will. They tell us about specific wavelengths of light, and something like the element hydrogen, or the element sodium, or the element potassium is going to absorb or emit light at the exact same wavelengths, whether that star is right nearby us, like our sun, or is literally billions of light years away. It's going to be emitting the same exact wavelengths. That's the amazing thing. And so whether they're in absorption or emission, they have the same wavelength. And that can tell us things like how fast an object is moving towards us or away from us. Now, the absorption lines we see a lot in stars, because as light is passing through the stellar atmosphere or the solar atmosphere, if we're looking at the sun, that light is absorbed as it's leaving the sun. And so that's very common in stars. Because galaxies are made of billions of stars, they have similar spectra. Where you often get emission lines is when you've heated up gas, either in the atmosphere of a star or in a galaxy, a cloud of gas in the galaxy, maybe you've heated up to very high temperatures, tens of thousands or tens of thousands of degrees. And when you've heated it up, you've excited all those electrons, sometimes to the point where they've actually ionized, they've left their atoms, and then as they come back to their atoms, they cascade down through all those different transitions, and they produce emission lines. So usually the difference between absorption and emission is telling us something about the presence, usually, of very hot gas. It can be a cloud of gas that's been heated from recent star formation. So a place in a galaxy where new stars are being formed, those are places you would find emission lines. It could be the remnant of a supernova. So a supernova is a very explosive and hot event, which gives off emission lines. One of the things I study in my research is emission lines in the coolest stars in our galaxy, which actually shouldn't have emission lines because they're cold, but their upper atmospheres get superheated by magnetic fields. And so they actually, some of them, which we call active, have actually emission lines. And that tells us that the very upper atmosphere of these stars has been superheated. And we use that in my group to do a variety of different things. So yeah, they get used for very similar purposes. They're tracers, again, of specific wavelengths, of velocity, but they physically tell us very different things. Again, with emission lines, really mostly telling us about the presence of really hot things.
All right, so the next question is actually two questions. The first one is, somewhere you mentioned that TESS is the biggest and baddest of all. Why so? Is it because it will spew out so much data? Also, how does TESS/Kepler function? They do not have optical telescopes, right? Just with a camera and a spectrometer/photometer?
Wow, okay, that's lots of questions. So I may have to like break those down into other pieces. So TESS, biggest and baddest. I mean, TESS, which is this new spacecraft that's going to be launched just in a few years. It's being actually built and managed by a team of people over at MIT, which I can see literally out my window here at Boston University. But myself and actually another one of my colleagues here at BU are actually on the TESS team because we're very interested in the stars and the exoplanets that TESS is going to find. And TESS is probably not really the biggest and baddest. It's actually a relatively small telescope. But one of the things that it's going to be the baddest at, and I mean that in a good sense, that it's going to be really, really good at detecting planets around nearby stars. It's not going to be very good at finding them around distant stars that are dim because it's actually kind of small. For a telescope in space, but it's going to be able to scan a number of nearby stars in the sky and detect nearby transiting planets around them. So unlike Kepler, which was really just staring at the same field of the sky, and actually most of the stars in the Kepler field are very far away, hundreds if not thousands of light years away. And Kepler did an amazing job at finding planets around those stars. Those stars, because they're so far away, it's really hard to do much follow-up observations of them and actually know the most about them. But stars near to our sun in the galaxy, actually we can learn a lot more about. And TESS has the ability, and will look at all over the sky to find planets around the nearest stars. So at the end of the TESS mission, we will actually know many of the stars that are really our neighbors in the galaxy, which ones of those host planets? So that's one question.
I think the next one is, how do TESS/Kepler function? They do not have optical telescopes, right? Just a camera and a spectrometer/photometer?
Oh, so the question is, how do they function? How do TESS and Kepler function? They actually do have telescopes. I mean, both of them are Kepler's one telescope that focuses the light from the telescope onto a giant detector, a giant, basically, camera that takes a picture. Yeah, it's like a big telescope that focuses all the light onto one giant frame that is taking an image, really, of a really, really big patch of sky over and over and over again. TESS works similarly, although it's actually 4 cameras that are staring at 4 different places at one time, and the light, it's 4 different telescopes, and the light from those 4 telescopes is actually then also being projected onto 4 different cameras that will then take the light and also from all the individual stars that it's going to see. So it is a detector behind a telescope. There is no spectrograph on either telescopes. They are just taking images of stars over and over, and they're doing it in the optical. So that was the other question, are they in the visual or optical? And both Kepler and TESS are basically the entire optical bandpass.
Okay, so this is the second question from the same person.
Yeah.
Although I never stop being amazed at human ingenuity.
Was there not another one?
What?
There wasn't another piece of that?
No.
No? Okay.
Just, they asked just with a camera and a spectrometer.
Okay, so no, so just a camera. Okay.
So although I never stop being amazed at human ingenuity at creating new and novel instruments and technology, where do you think this research will go in the next 10 to 15 years? Assuming that we have located a planet that has an atmosphere, assuming that we have discovered some signature of life, then what?
Oh, good question. I mean, the question is kind of where are we going to go from here? And kind of the question leads by asking, or assuming that we're going to, in the next 10 to 15 years, find planets that have atmospheres, which we've already done, and that some of those atmospheres may be look like they're habitable, and some may even look like they're inhabited. We may see like tracers of at least life as we know it on Earth. Now, we don't know if we're going to find that, but with the combination of missions like TESS, which will identify new planets and that are nearby and easier to study, and actually a combination of things like spectrographs on the James Webb Space Telescope, so the kind of next large space-based telescope that will be coming out of NASA, and that will be launched probably around the same time as TESS, but probably a couple years after TESS, to be honest. It will have the capability of actually detecting the atmospheres around the planets that TESS discovers. And if those planets have atmospheres that contain things that we think might be tracers of life, things like oxygen and methane, which on Earth are, most of the oxygen in the atmosphere is actually from life. And the combination of oxygen and methane together doesn't really happen on Earth unless there's life. Those two things actually like to combine very easily. And so unless those are being produced easily by things like life, you wouldn't get them separately. And so seeing those in the atmosphere of an exoplanet would be a very good indication that there likely is life. Is it absolute proof? No. So what's next after that? I don't know. My guess is that we would maybe try to send a message. There'd be at least discussion and debate about that. My guess is there'd be discussion and debate depending on how close the star is of actually sending a probe. And that probe actually, at our current technology, might take tens of thousands of years to get there. But I bet there would be discussion about that. There certainly would be a lot more study of that world, right? If we found stuff, I mean, there would be telescopes probably always pointed at that probe, trying to find everything we know about the planet, other planets in the system, the star itself. But I imagine a huge number of resources would be focused on that world should we find it. So, and who knows? I mean, as the question stated, we live in an era where technology is still rapidly advancing. Who knows what we'll be able to do in 10 or 15 years? Who knows what advances we'll make in the study of exoplanets? And who knows what clever people who maybe are just coming through grade school now what new ideas and new techniques they'll develop to help us understand these amazing environments. So some of it is, I don't know. I mean, we'll look back on this class and this maybe office hours 10 to 15 years from now, knowing stuff that's totally different than what we know now. So, and that's the fun of science.
Okay, so the next question from the discussion is about transits in Kepler.
Yeah.
It says, Kepler uses a number of very high-resolution CCDs to detect stars. Question 1, is any individual star detected on one or many pixels on the CCD?
Good question. So the question is about the detector itself behind Kepler, and says that Kepler uses a fairly high-resolution camera. What they mean by that is that it is able to detect precise points of light. It's actually not true. Kepler's actually got pretty crummy resolution. So the question was asking, do you sometimes get stars that are on multiple pixels? And the answer is very rarely, because the resolution is so bad and the pixels are so big that it's very rare to get that. Although it does happen a little bit, that just, you have a star that's on the edge of a pixel and it bleeds into multiple ones. What's more problematic sometimes is that you get multiple stars on the same pixel because the resolution is so bad. So it's actually kind of the opposite problem, that the resolution is so crummy, and that's actually just not because the technology is, well, actually it is a technology limit. We can build a Hubble Space Telescope level camera where we have beautiful resolution. You can see, the most precise things. You can see disks around stars. You can actually image them, which is spectacular. But one of the things that Kepler wanted to do is it wanted to pull down the data from hundreds of thousands of pixels at the same time, and that required a giant amount of bandwidth to be able to send that information back and forth to Earth, and it was actually limited by how much it could do. And if you made more pixels, if you made a higher resolution and had more pixels, you'd have to send more data. In fact, if you made it just twice the resolution, that would actually be, or if you made the pixels, sorry, half the size, that would actually be 4 times, because it's a square, the number of pixels you'd have to send down. If you did it 4 times, it'd be 16 times more data you'd have to send. So there's a limitation in how much data you could send back and forth to the spacecraft. So that was the decision that was made. So if there's a follow-up question there.
Yes. Any drift of the telescope will move the star's image across different pixels. What sort of data or image processing is used to correct for this so that the brightness of a star is accurately tracked?
It's a cool question. So the question is that, if you do have a star on multiple pixels, or maybe even 2 stars in a pixel, or if the spacecraft itself drifts a little bit, moves so that the position of the star doesn't stay not only in the same pixel, which actually would be pretty easy, but actually even moves in the pixel, that actually does make a difference if you're taking very precise measurements of the star's light. And so the question is, what types of techniques do you use for accounting for that? And what's actually done is a couple very clever people actually have developed software that actually figures out how to correct all of the Kepler data for things like that. Because the telescope actually in its current mode actually does drift a little bit. And that does affect the brightness of stars. And so what you can do is you can look at some stars that you don't think very, very much, and you do that kind of statistically. You can actually see what that drift is as a function of time and where the star is exactly on the pixel, and you can actually correct for that. And there's some again, there's actually not one right way to do that. There's a group at Harvard who's working on it. There's a group at NYU I know that's working on it. There's a group in Oxford working on it. And all of them do slightly different things, all of which work remarkably well, but differently. And so you have to use these very clever, some really highly mathematical techniques in order to correct for that. That's a cool question.
I just want to make sure people know how to ask questions.
Oh, okay.
Do you think you could, you press on this button up here, and then you go to the Q&A.
Okay. Rora wanted me to remind you, those of you watching, if you have a question, you can post the question by going to the upper right-hand corner of your screen, somewhere probably up here, and pressing the button. Looks like a little grid, and when you press that, you can hit Q&A, and it opens a panel on the right-hand side where you can actually post a question. So if you're watching right now and want to ask a question, please follow those instructions and let us know.
So I'm going to go back to questions that we didn't have time to answer or didn't see in time from the first office hours.
Sounds great.
So somebody asked, what is the frame of reference used for categorizing the direction of planetary orbits as clockwise or counterclockwise? Does it depend solely on the angle we observe them?
Oh, wow. So the question is about categorizing planets moving clockwise or counterclockwise. So, I mean, part of that is probably very sociological, in that, from our perspective, the Earth is, and all of the planets in our own solar system are orbiting the sun counterclockwise. I have to do the right hand here. They're going counterclockwise, and you might ask, okay, well, why, if you looked at it kind of upside down, it would look clockwise, right? But of course, this system was developed by people in the northern hemisphere, and so people in the northern hemisphere kind of see our orientation kind of up and down like this, and they say up is, you know, from the northern hemisphere perspective, and south would be the down. And so from that perspective, the northern part of the solar system is where the majority is in the northern hemisphere, and that's the up, and the down is the majority that's in the southern hemisphere. Solar system is actually a little tilted. The path the planets are tilted with respect to the Earth's tilt. But there's a big chunk that's in the northern hemisphere and a big chunk that's in the southern hemisphere. And so that's how the orientation, and then therefore the direction. If you decide an up and a down, then if you're looking down on the solar system from what you've defined as the top, all the planets look like they're going counterclockwise. So usually you have to first define a system. And so for our own solar system, it's probably defined by very sociological reasons and historical reasons, that it was the people living in the northern hemisphere who first defined that. Certainly when we go to other solar systems, you also have to choose kind of a direction if you're going to do that. It can be a bunch of different things. Usually it's based on the can be based on the orientation of the star, which often is you know, kind of orbiting in a similar direction of the planets. But it turns out, although we won't have a lot of time to talk about it in this class, that's not always the case. And so that is, I think that answers the question. Most of what it is actually just, it's not, there's not a good scientific answer or mathematical answer. It really is a kind of a choice answer. So we do think that the orientations of stars and the orientations of planetary systems are pretty random throughout the galaxy. So there's no evidence that there's an organized orientation of stars and planets in the galaxy. So even though the galaxy ourselves we live in is flat like a frisbee, it's, you know, the spiral type galaxy, the orientations of stars appear to be pretty random. And that's probably just a product of the star formation process, that it is the collapse of the clouds and how they rotate is pretty randomized.
Okay, so we've gotten now some questions in the office hours. So cool. The first one said, how far have we advanced in answering some of the parameters of the Drake equation? Oh, okay, cool. So how far have we advanced in getting the parameters of the Drake equation? That is a topic that I'll answer now, but it's actually a subject of Module 9, if I remember. When we actually talk about life in the universe, we will revisit the Drake equation. For those of you who don't know what the Drake equation is, it's an equation that was, or an idea really, if you will, that was formulated by Frank Drake, who was an astronomer in the 1960s. And he wanted to, like, just as a thought experiment, try to understand how many alien civilizations could be out there that could have the ability to communicate with us. That was what he wanted, to just do an estimate. And so in order to do that, he said, what were the things you would need to know? And so he wrote down a bunch of parameters. And they were things like how many stars are out there and what's the rate that stars get born in the galaxy. How many of those stars have planets? How many of those stars have planets that you could actually be habitable? You know, how many of those that then are habitable have life? How much of that life becomes intelligent? How much of that intelligent life becomes technological? Because you need to be technological in order to communicate. And then I remember the last term is kind of fun and also pretty sociological for the time. It was the lifetime of the civilization. And of course, one of the things that was happening in the 1960s was, you know, the Cold War and Bay of Pigs invasion and things like that. So there was a lot of fear that, you know, when societies became technological, they might just blow themselves up. You know, they learn how to make nuclear devices and then they destroy themselves.
And so that there's a piece of that sociology in the Drake equation. But the question is, how far have we gone? Well, we know a lot about how stars form in the galaxy. So we could tell you how many stars of what type form and about how often they form. For the first time in human history, we can actually probably tell you now the number of planets, right? And we know amazingly from missions like Kepler that they are really common, that probably almost every star in the galaxy statistically has at least a planet, probably a couple planets, and that planets just are very, very common. We even are at the point where we're starting to be able to answer the next parameter, which is how many kind of are habitable, how many are small planets, terrestrial planets that you could step on, that you could live on, that you could have liquid water on. I think we're getting at a place, but those are also not terribly uncommon, that habitable planets are, there are billions, tens of billions, maybe even 100 billion in our galaxy. I mean, pretty common. The parts we don't know about yet are the ones that all follow that. We don't know how common life is. We don't know if we did develop life in other planets, even in our own solar system or in other solar systems, how often, if ever, do they become intelligent? We have a whole debate about what intelligence is. What happens? How often do intelligent beings become technological? I mean, you could make a strong argument that creatures like chimpanzees, or especially maybe dolphins on our planet, are actually intelligent, but they're not technological. They could not, as far as we know, communicate with alien civilizations. So despite being very advanced creatures and having communication and probably intense and very detailed thought processes, they don't have technology that would allow them to communicate. So we'll talk a lot more about in that Module 9. Cool question, because we know a lot more about the Drake equation just in the last few years than we did even when I was in graduate school 10 years ago. So cool.
The next question from the discussion forum is, this is from Google Hangout.
Yeah.
We looked at the transit technique. Are you going to be covering other techniques in other lectures?
Oh, yeah. So this newest module is the transit technique, but we will be reviewing at least the other major technique, which is called the radial velocity, or the Doppler technique, or the wobble technique. Has all those names, but we call it the radial velocity technique. And we'll learn more about it. I think that's module. Oh, it's module 5? Or 6, 5? Okay. It's one of the next modules. We won't talk about some of the other methods in detail. I'll briefly mention there's a method called direct detection, which is kind of like it sounds. You literally go out and take images of planets. And so for the first time, just in the last 5 years or so, we've been able to actually image a few planets around stars. We have to do some clever techniques for removing the light of the star, or at least making it dimmer. But we're able to do that, and the technology for that is greatly improving. There's a couple other techniques that we're not going to talk about very much. There's one that's called microlensing, where through a very interesting effect of gravity, you actually can turn an object into a massive object into a little bit of a lens that actually magnifies it a little bit. And so if you have a star that passes in front of a background star with a planet, you can actually get the light from that planet and star and planet brighten just a little bit. And that's called a microlensing event. And there's been some planets discovered in that way. The other kind of cool way, which now that those of you who have watched and done the transit stuff know about, there's one that's called the transit timing detection. And this is actually another indirect method, which means we don't see the planet itself. What we do is we watch transits happen. And the planet goes around and blocks light from the star, and the planet goes around and blocks light from the star. But if we time that, and we know Kepler's laws, we would say, like, okay, well, it's going to go around like clockwork. And say it has a period of a few days, every few days, it's going to pass in front. But if we pay really, really, really careful attention to when the transits happen, we can notice for some of them, it doesn't happen exactly at the same time every time. And that means there's something wrong. Either something else is happening or Kepler's laws are wrong. We don't think Kepler's laws are wrong. So we think is happening in those cases that there's another planet in the system that's actually tugging on that other planet just a little bit to affect its rotation around the star. And so the timing in the transit happening, if the timing is not perfect, clockwork, that usually is evidence that there's at least another planet in the system that's tugging. And based on how much it's tugging, it actually tells us that there is another planet, where that planet is, like how far away from the star, and actually how massive it is. So that can be a very powerful technique, and there's been a few planets that have been discovered in that way. So we won't talk much about that, but I will introduce the radial velocity, which is really the first main method for this.
This is back to the discussion forum for the first week.
Cool.
If you had to guess now, does Ceres have a fairly solid interior or a liquid ocean? Do you think Dawn will be able to determine which is the actual case?
Oh, that's a great question. This is about the Dawn mission, which is looking at the asteroid, or now I guess minor planet Ceres. Ceres is an object. It's the largest asteroid in the asteroid belt. It's the material that's between Mars and Jupiter. It's basically the remnants of a planet that never formed. Probably was enough material between Mars and Jupiter to form another, probably terrestrial planet. But it turns out Jupiter was a big bully. Jupiter was not only its big gravity, but actually the newest models of how planets form actually indicate that maybe Jupiter and Saturn actually migrated really in close to the inner solar system, and actually not only didn't allow a planet to form where the asteroid belt is, but actually made Mars be much, much, much smaller than it is. And then they actually migrated back out to where they are today. That's called the Grand Tack scenario. That's actually one of the most widely accepted ways on how our planets formed in our solar system. And we'll talk more about planet migration in the next couple modules, because that actually is important for some of the exoplanets that we see around other stars. We have strong evidence that migration must happen to form planets the way that we think planets form. So Ceres is this large asteroid in the asteroid belt. Ceres used to be a planet, a lot like Pluto. In the 1800s, when Ceres was first discovered, people called it a planet. And then, very similarly to the Pluto story, Ceres was found to just be one of, now hundreds of thousands of asteroids floating between Mars and Jupiter. And so instead of having hundreds of thousands of planets, they just demoted it, sound familiar, to what's called an asteroid. And actually, although lots of people still, complain that Pluto's not a planet, it's a minor planet now, or dwarf planet. Sorry, a dwarf planet. Ceres actually won in the whole discussion, because Ceres became a dwarf planet in the whole Pluto saga. Pluto was demoted from planet to dwarf planet, but Ceres was elevated from asteroid to dwarf planet. And there's this mission on the way there. There are some weird spots on the surface. Looks like maybe ice, or we don't actually know what they were. And the question really is about, are we going to be able to tell the internal structure? Are we going to be able to tell if there's liquid water maybe, and some people think there might be? The answer is yes. After probably a lot of study, we will be able to understand the interior of Ceres. And you might ask, how can you do that? You can't see, it's a big ball of rock and ice. The way we can actually do it is by studying carefully how it rotates. And this is something we didn't have a lot of time to do in this version of Alien Worlds. But sometimes when I teach this class here at Boston University, we talk about this technique. And if you actually look at how things rotate, that tells you something about their internal structure. And most of you watching this probably know this. You know that when an ice skater is twirling, and at the end of their routine, they have their arms out like this, and they're spinning, and then they move their arms in, they start spinning much faster, right? They haven't actually changed the amount of force or anything they're doing, but by putting their mass from much farther out to much farther in, they actually start rotating faster. That's called the conservation of angular momentum. Well, the same thing happens with planets. As they actually go through small gravitational interactions, their rotation rates change a tiny bit. This happens actually on the Earth due to interactions with the moon. It happens to Ceres with interactions from other asteroids. And the amount that that rotation changes actually tells us something about how the mass is distributed through the star, and actually something about the density profile of that, at least loosely. And so I think we will actually have some idea of some of the internal structure of Ceres, not in great detail, but enough to probably make some predictions for what interior looks like, based on calculating what's called moment of inertia. That's the physics term for it. And we get that by looking at how, again, it rotates, how its rotation changes actually a little bit. The real way to do it, and the way this is done on Earth, or actually in the sun, and actually soon it will be done on Mars, is actually to land something on the surface, have things that detect, like seismic waves. And actually, as those waves pass through the surface, through the center of the object, as they pass through material of different densities, waves move at different speeds. And so that allows us to actually map the interior. That's actually how we know what the interior of the Earth looks like, is by actually earthquakes, or actually nuclear blasts, things like that. How those waves propagate through the Earth tell us what the inside of the Earth is made of. And we've actually done some measurements that on the moon as well. Turns out we do that on the sun as well through a technique called helioseismology. You can actually do it on other stars in a technique that's called astroseismology. And we've begun to do it on, there's a project to do it on the planet Mars, which will be very exciting.
That's all the questions we have now.
Okay. I have a question that I got on my email.
Awesome.
From the Google+, but I want to take one question, one break really quick, just to actually grab the plug for my laptop, which I didn't have time to plug in, so we had to switch laptops due to a technical situation. I'm going to grab that really quickly. Anything else in discussion? All right.
That's all the questions from the last two discussions.
Okay, I am back. All right, I'm going to look up this question. So the question is, all right, it says, in Module 1, Introduction Lecture Video, you said that stars we see in the night are what they were 4 years ago and not what they are today. And the time obviously will differ with different stars as they're at different distances away from us. So the question is, astronomers predict our future by making calculations from stars, but how can they predict it as the stars we're seeing now are only just images of what they were 4 years ago? Wow, so we're looking into the past, and so we don't really know what the present is for really any stars in absolute time. How do we make a prediction of the future? Well, a couple reasons. One, something like the nearest star being 4 light years away and looking at it as it's 4 years in the past, that's essentially looking at it as it is today. Stars like our sun, remember, last 10 billion years. They're alive for 10 billion years. So the difference between 10 billion and 4 is very, very tiny. It's a very tiny difference. And so, looking at something as it was 4 years ago isn't actually very different. That gets a little more challenging if we were to look at stars that were thousands or billions, or not thousands, but millions or maybe billions of light years away. But it's actually very hard to see individual stars. It's impossible to see individual stars that are billions of light years away because there wouldn't be enough light to detect them. We see galaxies, which are made up of hundreds of billions of stars that are billions of light years away, and those tell us something. But we also know how the physics looks. We know that how stars burn fuse their energy. We know how that process works, and that can help us understand when a star will actually run out of fuel. So, for example, the types of stars that I study, these little tiny M-dwarf stars, they have lifetimes that are measured in hundreds of billions or trillions of years. Now, that's longer than the age of the universe. So we haven't been around long enough for one of these tiny little stars to ever die. And yet we can say to some level of certainty that these stars last that long. And that's just because we know how much gas they're using right now. We know how much fuel they have in the tank. And so we can kind of play the movie forward, and we can say, okay, well, if they're using about this much gas, they have this big of a tank, here's how long they'll last. Just like many of you have cars that tell you how many miles you can drive till empty, or you know that like you can go so many miles in your car. You know that because you know about how efficient your car is, you know how much gas fits in the gas tank, and so then you know how long you can go. The same exact thing is about stars. So we can actually predict some of the future by looking at the past. Huh. Cool.
There's a new question now in Google Hangout.
All right.
It says, with the transit technique, how do you eliminate star spots as false positives?
Cool question. Yeah, so how do we eliminate star spots as false positives? So it turns out that the details of a transit and the exact shape of the curve is not the exact nice like rectangle that I used in many of the examples. In fact, those of you who did the challenge or do the challenge problems for the transit technique will actually see a much more realistic shape of what the transit looks like. And it turns out that is actually quite a bit different than what a spot looks like. A spot on a star actually has a dim part and actually a bright part. And so it actually gives a very characteristic signature in the dip it makes. It still makes a brightness dip in the star. It changes the brightness of the star, but it's actually quite different than what a transit looks like. So the way we actually tell those things is by looking at the exact characteristic shape of the signature, and that tells us something about it. We still actually want to be sure, so that's why we actually monitor many times and make sure that we can both see the dip happen the same time every time. Star spots will come and go. They aren't, I mean, on the sun, they might last days to weeks, sometimes maybe a little bit longer. Planets are still there over and over again. So that's one easy way to differentiate between a star spot. But the exact shape of that dip can look different. And for those of you who are interested, just give a look at the challenge problems, which actually will show you what kind of a more realistic dip of the transit is. That's a really great question. Anything else? No. I think I had another question, maybe.
Okay, good.
Let's see, it just came in. Oh, I think it's the same one. It is the same one, they just repeated it. Any more questions from the audience, whether it's in the Google Hangouts or in the discussion section? Anything else from specific questions about the material and or the assessments or things like that? One of the exciting things that Aurora and I are working on right now for her main research project, we'll tell you a little bit more next week because, and you'll see this in one of the, probably our video, weekly video emails, is next week Aurora and I are going to a conference in Baltimore at the home of the Hubble Space Telescope Science Institute. So the Space Telescope Science Institute is hosting a conference on basically the exact science that Aurora is working on, something called the initial mass function, which tells you the number of stars as a function of mass that are formed in a burst of star formation. And so we're going to a 2.5-day conference all about that. And Aurora is going to be presenting a poster, and I'm going to be, I guess I'm chairing one of the sessions. So I'm not doing nothing. I'm actually listening and learning, and I'll be chairing one of the sessions where people are giving talks. And we'll give you more information about that next week. But we're in the the last throes of putting together Aurora's poster for that. So we're both teaching alien worlds right now, but we're also trying to get some science accomplished, which is what we do. Anything else? Any other? I don't see any other new questions that have come in. Any more on the discussion section? Okay, we'll give it a couple more minutes just to see if there are other things that come in or other things that you're interested in before we end here. I'm just going to check and see if there's anything that has come in on my end here. Don't see anything. But we'll give you guys a couple minutes if there's any other last questions that you might have.
Yeah, I don't see anything there.
We'll give it a couple minutes.
Okay.
Any other good questions from the discussion that I haven't
I was
answered?
looking through them to see if there were any talking points on here. We can definitely talk about some of the things on here. Do you want to do that?
Sure, yeah. We'll spend the last few minutes, unless there are further questions, talking about some of the just general questions that have come up on the discussion forum. Aurora's been answering a lot of them. I've been answering them on occasion. We really appreciate those of you, some of whom I see are asking some of the questions here today, some of the help that you've had in helping answer other students' questions, but some of the questions that have been asked are really phenomenal. Oh, I just see a new question by Alex. Cool. So before we get there, I'll answer Alex's question, which is really a spectacular one. How easy or hard is it to detect exomoons using the transit technique? Oh, what a cool question, Alex. So exomoons, of course, would be a moon orbiting world. And so you can imagine you might actually see the transit signal, and then you actually might see a little dip if the moon passes in front of the star as well. So you actually might see like kind of a little extra dip. But you have to remember that, you know, if the Earth blocks about 1/10,000th of the light, I think I got that about right, of the sun, the moon is about 1/4 of the size of the Earth, roughly. And so if it's 1/4 of the radius, 1/4 of the size, that's 1/16th of the area that it's going to block. So that's 16, let's round it to 20 to make the math nice. So that's 20 times less blockage. So that's 200,000th of the brightness. So that's extremely, 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 extremely hard to see something that's like moon size blocking something that's sun size. Now, the moon is actually one of the largest moons in the solar system. I mean, there's Callisto, some of the Jupiter's moons are a little bit bigger, but to be honest, they're not a lot bigger. The moon is actually really, really, really big for its size. And that's actually part of, we think, how it was formed. It was formed probably by a kind of planet-sized collision with the Earth very early in the Earth's formation, kind of as it was forming or just after it had originally formed, collided with the moon, or collided with another object, and a bunch of really molten rock was actually spit off side of the Earth, and that actually formed the moon. This has actually been shown in simulations. Actually, I just saw a paper yesterday, a brand new paper, that showed that this was actually pretty easy to make. It's probably the only one of its it's the only example of that in our own solar system, but it's actually not a super hard thing to make in other solar systems. There's a lot of collisions that happen early on in a solar system's formation, and so some of the time you're going to get collisions that produce things like our moon, and it's very large, for at least the size of our planet. So 1/200,000th of the light, or even a 1/100,000th, it's a very hard thing to work on. Now, there are people working on this. There is a acquaintance and colleague of mine who's just going to be starting a faculty job at Columbia University. And he actually has an entire program to go through the Kepler data and actually look very, 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 very carefully for exomoons. As of right now, he has not found anything. But if someone is going to find it, at least in the Kepler data, it's probably going to be his research team. David Kipping is his name, and he's he's going to be he's looking at it, and one of the things he does to try to get down to the precision that you need for finding an exomoon is he actually combines many, many observations of a star at various different periods to try to actually get a detection, a possible detection. He hasn't found anything yet. Let's see. Oh, I got a. Did you get a new one?
Oh no, I was just going to say something about exomoons.
Oh, Aurora wanted to say something about exomoons.
I think somebody has found like rings around a exoplanet, so you can find some features, right?
It's a great point. Yeah, Aurora was referring to another paper where someone actually found evidence of maybe rings around an exoplanet, which would be like potentially like the material that either didn't form moons, or maybe it means there's moons outside of the ring systems, just like in the Saturn or Uranus systems. But the rings of Saturn are actually a lot like the asteroid belt. They're kind of a moon that never formed, or a satellite that never formed, due to the intense tides of Saturn really near its surface. So there wasn't enough, the tides were too strong for the gravity to coalesce and form a moon. This last, I think we'll see how long it takes me to answer it. Question I just got here on my phone is, I've heard that bacteria have survived on satellites in space. Also, we've found many Mars meteorites that are here on Earth. On that basis, Earth rocks should have reached Mars following volcanic or impact events. Hence, is it possible that visible Earth microorganisms have reached Mars many times over the last few billion years, perhaps when Mars was favorable for life, with time to adapt to harsher conditions over the millennia? Your thoughts, please. Awesome, awesome, awesome question. So it turns out it's easier for things to get from Mars to Earth than Earth to Mars for a variety of reasons. The way this happens, of course, is large impacts hit worlds all the time. Over the lifetime of the Earth, it's been bombarded by large impacts. Same thing happens to Mars, same thing happens on the Moon, same thing happens on Venus. We have evidence of meteorites on the Earth that come from asteroids. That's where most of the meteorites come from. I actually have one right here. Here's a meteorite. This rock used to be in outer space. This is an iron meteorite, so it probably comes from the core of a relatively large asteroid. Most of them come from the asteroid belt. We have evidence of meteorites that come from Mars, as this person suggested. And we actually have meteorites that come from the Moon. And we know that because we know that the rocks on the Moon and Mars are actually both a little different than stuff on Earth. And we know what those look like because we've been to both worlds. The humans been to the Moon, and we've had lots of robots and rovers and all sorts of stuff being on the surface of Mars. But again, it's much harder to get something from Earth to Mars because Earth has a lot more gravity. All right, so Earth is a little bit larger, which makes it actually, remember, have less gravity, but it's a lot more massive. It's about 10 times the mass of Mars. And so that actually makes it have quite a bit, more than twice the gravity of Mars. So it's actually harder for something to get off the surface of the Earth and all the way to Mars. Also, the thick atmosphere, relatively thick atmosphere of Earth makes small things that are harder to get out of the atmosphere of Earth. That doesn't mean things don't. It turns out I have a friend who actually thought of this same question and actually did a little experiment where he actually simulated impacts hitting the Earth and where the material from the Earth would go. And it turns out that it was really hard to get a lot of material to Mars. Maybe you could get a little bit, but not very much. But it turns out you could get a lot of material to the Moon. Moon's nearby. It was actually pretty easy to get Earth rocks on the Moon. So one could imagine that, you know, if life was developing in the first billion years or so of Earth's existence and you had large impacts happening, the very first Earth fossils could actually be on the Moon. How cool is that? That's pretty cool. Probably very hard to get material all the way to Mars. And certainly enough material that would have bacteria. Is it impossible? No. It's a really cool idea. Maybe it happened. Really, really neat idea. But getting it to the Moon is actually pretty easy. Very possible to get to the Moon. And of course, again, the reverse happens. Also probably easier to get to Venus. Venus is closer. Also has a lot of gravity. Really hard to get things off Venus. Venus has about the same gravity as Earth, but it's got, you know, an atmosphere that's 90 times the atmospheric pressure of the Earth. So really thick. It's really hard to get much off the surface of Venus, both through the thickness of the atmosphere and the relatively strong gravity. Cool. I think with that, we have finished our hour. I thank you for all of your questions. Thank you for attending. Hope you have an opportunity to watch this on YouTube or when Aurora posts it to the course page. And we'll talk to you at the next office hours. Oh, one thing I want to say, we will not have an office hours next week. And I'll send this in an email, but I'm actually got asked to do a Reddit AMA. If you don't know what that is, it's an Ask Me Anything. I will be doing that next week, and I'll send you more information on Thursday. Ooh, I saw a really quick question that just popped up by Alex. Earth rocks on the Moon might have evidence of the early atmosphere of Earth. Absolutely. Yeah, rocks trap their atmosphere in them. So actually one of the reasons we know Mars meteorites are from Mars is actually that inside the crystalline structure of the rock is actually trapped the Martian atmosphere. And so absolutely, if you could identify an Earth rock on the surface of the Moon, you could actually see what the early Earth's atmosphere was. So really, really awesome question. Cool. All right, until next time, stay curious.